the only distinction about multi-body problems as is separate from single-body problems is the fact that we now have a system of objects that are somehow connected, and generally connected through some force. The thing that I need to emphasize is that there's a lot of ways to go about describing this, and some are definitely better than others. What I'd really wish to do is to make the distinctions about what it means to be a multi-body problem and some of the vocabulary around it. I'm going to kind of start there from the beginning. A multi-body problem is just a problem in which two or more objects are somehow connected together in a way in which the motion of one somehow influences the motion of another. It's a multi-body problem, which is the most generic definition I could probably give you. I'll say again, it's just some kind of problem in which you have two or more objects where the motion of one object is connected in some way to the motion of another. This is not how I explain it in AP Physics 1. I tend to be more directed and grounded, but there are so many different variations of this that I don't want to sell ourselves with just this one. The thing that you have to consider in any multi-body problem is how are the objects connected? That's the first thing you need to consider. And do they share any properties of motion together? For example, if I say to you that we're going to push on this system from this side and apply a force to this side, unless one of the boxes collapses, the motion of these two objects is going to be connected. In fact, I don't think it's too unlikely to say that these two objects will probably share the same motion, perhaps the same acceleration, definitely the same velocity. And that has to occur, or else one object passes into the other, or the two objects separate. Now, there are a variety of forces I think that all of you could probably indicate are acting in this system. But we should consider that there are now what are called internal forces and external forces. Newton's second law was all about internal forces. I'm sorry, I said that wrong. Newton's second law was all about external forces. But internal forces act within a system. Generally, internal forces are Newton's third law pairs of forces. For example, in this, what we've drawn right here, it's two objects. So if you'll recall in our discussion, whenever we're going to deal with this using force, we would have to deal with it from the standpoint of looking at one object at a time. So let's say that I have object 1, mass 1, and object 2, mass 2. And there is an applied force acting on object 1 to the right. Let's just, for the time being, make this frictionless. Can you identify all of the forces acting on each mass in this problem? Take a minute and do so, please. I'm sure with all the heroes and villains in the room, I could probably pick on any one of these superheroes, especially the Iron Lantern, for he is so powerful with his mighty light and all, and his ring. He'll probably help us out. Don't worry, Kim Possible will try too, I'm sure. All right, enough time. Iron Man, give me some forces acting on M1. Not Iron Man, I'm sorry. Green Lantern, give me some forces acting on M1.
Weight.
All right, so weight. So I assume you mean M1G. Great. Now, I want to be careful. I'm going to say normal force, but I think there's going to be more than one normal force in this problem. Would you agree? So how do you want me to label this? N1, that's fine. Next?
And then force applied.
Force applied, sure. Anything else? I think there is. I think M1 is in contact with M2. So if there's two surfaces in contact, shouldn't there be another normal force?
Yeah.
I believe so. So that's why I was trying to be specific about how I label N, but I am pretty sure that based on our definition of normal force, there would have to be a normal force this direction, acting on M1 from M2. So I don't know how to label this, but I'm going to say normal force on 1 from 2. You guys do remember how that list works, right? Just walk down it. Any surface in contact applies a force. That force has to be perpendicular to the surface in contact. So, Kim Possible, tell me the forces on M2.
On F2, it's going to be normal force 1 going up, and then it's going to be mg.
I'm going to call that normal force 2 because it acts on box 2.
Okay. And then there's m2g going downwards. And then normal force 2-1 going in the opposite direction of the other one, so going right. It's going to be n2-1, and then force applied 2-1.
Nope, I think this is all it's acting on that box. The applied force only acts on box 1. Doesn't act on box 2. And here's the thing, remember, when we deal with forces like this, unless it's a fundamental force, it must be in contact with the object in order to be applied. So this force isn't directly applied to box 2. It gets applied to box 2 due to the normal force that's created because one box is being pushed into the other. Everybody follow along? In fact, it is that internal force that is transferring part of this applied force over to the other box. But your rules for dealing with forces don't change. If there's a little guy here that's doing the pushing, then he can only touch box 1 if he's applying the force to box 1. Now, you still have a set of rules on how to deal with a group of forces. Those rules don't change. The only difference is that we now have more objects to deal with. Is it possible for box 1 to move to the right without box 2 moving? I'm not trying to make this hard. That would only occur if box 2 is collapsing or box 1 is being pushed through box 2. So for the most part, I think we'd say whatever motion box 1 makes to the right, box 2 is making to the right as well. You guys follow along? Frictionless surface suggests the system's going to accelerate. I'm going to assume this is a second law problem. So we apply our rules. We have a variety of rules. Let's start with box 1. I'm going to make to the right positive. And here's one addendum to your list of things. It's not really an addendum. It's just something I would consider. I would make the positive direction the direction of the likely acceleration. I think both boxes will accelerate to the right. I'm going to make to the right positive for both boxes. So box 1, net force in the y direction, 0. So N1 equals M1G. Not a surprise. But net force in the x direction equals, and be careful here, you're going to screw this up, and I don't want you to. It's M1G. We're dealing with box 1, so use box 1's mass here. Be careful about that stuff. You will make this mistake. I'm trying to make sure you don't. So think about it. Write it into your notes. Make sure you understand. Newton's second law applies to an object or a system. So it needs to be the mass of the object or the mass of the system. Nothing generic. We're dealing with box 1 right now, so it's box 1's mass here. And it looks to me like there are two forces acting on box 1 in the horizontal direction. The applied force and one of the normal forces.
Wait, is it not supposed to be M1A?
Why is
It is M1A. Let's go to the other box. Net force in the y direction equals 0. So N2 equals M2G. But net force in the x direction equals M2A. I see only one force to the right. N21 equals M2A. It is Newton's third law that says that these two forces have to be equal and opposite. We've already dealt with the opposite part. Right, that part we've dealt with. But the fact that they're equal, we need to deal with that too. I think because they're equal, we just drop the subscript. They are equal forces. I don't need to worry about the direction. I took direction into account already. Now here's the only difference in dealing with a multi-body problem versus a single body problem. When you make it to here, you are generating relationships that basically deal with both objects at once. They are, in effect, simultaneous. So this is a set of forces that act on box 1, and this is a set of forces that acts on box 2. I'm not particularly interested in the y direction because there's no friction, and those canceled out to be 0. These are the forces that deal with the motion of the system. Now, there's a lot of things we might be interested in. We might want to know what this normal force is. Like, is one of the boxes going to crush the other box? Can it withstand this amount of force? That'd be by determining what this normal force is. Maybe we want to know what the acceleration of the system is. That's another thing we want to determine, but this is all that Newton's laws do. They boil it down to a couple of relationships that perhaps you can use to figure something out. I'd like to figure out the acceleration. I think that's not an unreasonable thing to ask about. So let's figure out the acceleration, and to do so, I don't have it, nor do I need it. I want to get rid of the normal force. It's in both of them here. I could do substitution. Some of you would probably prefer substitution, but I want to show you something else you can do. You can just add the two equations together. I'm doing that because I know that I have a positive n and then negative n. And if I add these two things together, those will just cancel out. When I do that, I will get just the applied force on one side. On the other side, I'll get m1a plus m2a. Now pay attention, this is important. And I don't say this lightly. Factor out the a. Newton's second law says the net force, the unbalanced external net force, will be equal to the mass times the acceleration. This applies to a system. Notice we have the full mass of the system here. The only real external force acting on the system that's not being balanced by something else is the applied force. The normal force was an internal force. That's why it canceled out here. When you're working a multi-body problem, there will almost always come a time where you will get whatever the applied force is that's external to the system, the sum of all the masses, and the acceleration. It will almost always show up. In fact, if it doesn't, you've likely screwed something up. I do want to point out that if you were interested in the normal force, you would have to get it from here. Meaning you would have to take this, find the acceleration, and then consider going backwards to find the normal force. And I want you to see this because most of you, still have some issues when we do math like this. So let's do the substitution. We'll get normal equals m2 times a, but a is all of this stuff. So I'll put the FA up there over m1 plus m2. And I want to reorganize this. reorganizing it because I want to make it very clear that a portion of the normal force gets passed through. A portion of the applied force gets passed through as the normal force. A portion does. Look at this. This is a percentage. It's the mass of one box divided by the mass of all the boxes. If M2 is bigger than M1, then a larger percentage of that applied force gets applied to box 2. Meaning the normal force will be bigger if you push on the smaller box. That's what it's saying. If you're trying to reduce the size of the normal force, you probably would want to push on the bigger box and have it be pushed into the smaller box. That would reduce the normal force between them. But if you push on the smaller box, you're going to ramp up the normal force. And I don't want to minimize this because I don't think you guys are seeing the big picture that I want to, but what's really happening to the box M1 is that M1 is being crushed. There's FA pushing this way, and there's a normal force pushing this way. It is being crushed. If the box can't withstand it, it'll collapse. So if you want to reduce this force and you need to move the boxes, well, it might be better for you to push on this side. The acceleration will be the same because nothing really has changed except now this normal force will have switched. And this would be M1 here, and this will be M1 there. I just did one of your homework questions. Those of you who took good notes, you're in good shape. Try it. There are a variety of these kinds of problems, some of them harder than others. I want to show you one that's a little bit harder than this one, but we're not going to work it all the way through. We're just going to set it up. I put 3 versions of this problem in your homework. We're going to say that there is a coefficient of static friction between the 2 boxes, but we're going to say that this surface, just to make this easier, has no friction. Now, here's the question, and it doesn't matter to me where we place this force. The amount of work is the same. And I ask both questions on your homework. I ask, how big a force can be applied here without this box sliding backwards? But I could just as easily ask, how big a force can be applied here without the top box being pushed off the bottom? I'll do one of these. They're both the same level of difficulty. Which one do you guys need to see? Do you want to push on the top box or push on the bottom one? Which one feels the most foreign to you? What's that? Wow, it's about 50-50 split. So I will do the one I've pictured now, the top one. This might be hard for you to fathom, but go ahead and take a minute and put together a free body diagram for each box. In the interest of time, let's say this is the top box, this is the bottom box. So in the interest of time, the top box is definitely experiencing an applied force. We know it's going to have its own weight. Let's make the top box MT for top. It's definitely going to experience a normal force. We'll say normal force on the top box. Any other forces acting on the top box? Friction. There will be a frictional force. Here you need to be careful. Friction tries to prevent one surface from sliding past the other. So we need to make sure that we understand that friction on the top box It's got to be in this direction. And it's static friction. I'm trying to prevent the box from sliding to the right. That means there must be a force to the left. Now, I assume on the bottom box, you realize that there's definitely a downward force due to gravity. We'll say M bottom times G. And definitely a normal force upwards. Normal force on the bottom box. I intentionally drew it longer because I also know there has to be a downwards normal force on the top box. I'm sorry, on the bottom box from the top box. Did you get that one? I hope so. Because that would definitely have something to do with any friction on the bottom box due to the ground. Be careful. We didn't include friction on the ground this time, but there would be friction from the ground, and you would have to account for it. But there's also a force acting this direction on that box, and that is also friction. It is friction that pushes the bottom box to the right. In fact, this is a Newton's third law pair. And this is a Newton's third law pair. There are two Newton's third law pairs that connect these two objects together. Be careful, though. The static frictional force created here is based on the normal force that is on the top box. Those two forces are equal and opposite, but it's based on the normal force on the top box. You should square that away in your thinking. Remember, friction comes from normal force, but the normal force that's acting between these two surfaces is due to the top box. Now, these, I think, are going to be unbalanced. So net force is going to equal M bottom times A, and net force here is going to be equal to M top times A. Now, here's where you need to really be paying attention to what was said in the problem. How big a force can you apply without the top box sliding off the bottom box? They're delivering information to you in code. The only way the top box doesn't slide off the bottom box is if they both have the same acceleration. That's what they're telling you there. Yeah, there's going to be other things involved, but they're telling you the two boxes will have to have the same acceleration. If one accelerates more than the other, then they're slipping. Do we understand? That's a condition. They're telling you the accelerations are the same. So, starting with this box, I think we can say the applied force minus the friction force equals MTA. And yeah, the top normal force is equal to MTG. And over here, we know the frictional force is equal to MBA. Now, here's the thing. You might think, well, I can answer the question. I just like we did the last problem, I can take these two things. Oops, I guess I can't take those two things. I could bring those two things together, and I could figure out the applied force, but you can't. This wouldn't figure out the applied force. This would tell you perhaps what the acceleration of the system is. It can tell you that. But this assumes you can push with any amount of force, and this is how much the acceleration would be. This does not tell you the size of the frictional force, which is the limiting factor. If you want to figure out the limiting factor, you're going to have to work in what is limiting the problem. And it is friction that is limiting the problem. Now, you may not know where to go from here. This is where it gets hard. This is the kind of stuff that's challenging, because this problem is asking you to figure out a limit, which means I think we need to get something into here. But we know part of this. We already know what our limiting factor is. We know that the normal force in the top box is equal to mtg. We need to figure out what the applied force maximum is. So we want to try and find a way to write this perhaps in terms of the applied force. Do you see a way to do so? If you don't, it's right here. We didn't need the acceleration. We were never asked what the acceleration was. We eliminated the frictional force in order to get the acceleration, but we should have eliminated the acceleration to get the frictional force. We can still do so. If I solve this for A, I can figure out the limits on the frictional force. Now that gives me an expression. It says that the frictional force is equal to mb over mt plus mb times the applied force. This is a lot. This is a tough question, which is why I wanted you to see it. And I'm going a little fast, but the only thing that's different than what we did earlier is what we did here. Everything else up to this point is the same as what we've been doing. It's just what we do with the information that's different. Now, yeah, there's a lot of algebra here, and we did a bunch of algebra. I think, doing some substitutions here wouldn't be a bad idea. If you want to know what the answer is, it's going to involve this. I think you can solve this for the applied force, because that would be the answer. It would tell you that the applied force will have to stay less than whatever that garbage is on the right. And there's a lot of it. All right, so we did an easy one. Now we just did a hard one. Who's up for another easy one? Another multi-body problem. How about we do your lab from yesterday? That's an easy one. All right, this look good enough to mimic your problem from yesterday? Or at least the lab from yesterday? You hung something off the table, measured the acceleration of the system. This has a special name, this kind of system. It's called a modified Atwood machine. So if you hear the phrase, modified Atwood, this is what they're talking about. A true Atwood machine would just hang a mass on either side of a pulley. This is a modified Atwood machine because we have a block or something that's resting on a surface and something that is hung on the other side of the pulley. Atwood machines generally have a pulley in the system. Later in the year, our pulleys are going to have mass. For the time being, we're going to say that our pulleys are massless, which means they have no inertia. This is important. It's an important distinction because that's not going to stay the case for very long. But knowing that a pulley is massless is telling you something else that you need to get down and make sure you understand. If you have a massless pulley, the tension in the string is the same everywhere. I'll say that again. If you have a massless pulley, the tension in the string is the same everywhere. Now, if you guys need to see this slower, I do just the Atwood machine in AP Physics 1 today. I'm not going to go particularly slow here because I think this is pretty straightforward for most of us. Let's use MC, mass of car, MH, mass hung. And just like we indicated in the lab yesterday, let's assume we're dealing with a system of low or no friction. Free body diagram. How many objects do we have? 2. Go ahead, draw a free body diagram. All right, let's start with the mass hung. How many arrows did you draw? 2. So, MHG. Did you draw a tension as well? Did you draw it upwards? Did you draw it less than the weight? I hope so. Didn't the box accelerate downwards? So the tension has to be less than the weight. How many arrows did you draw on the car? 3, good. So you draw a downward arrow to represent the weight of the car. Normal force represents the force from the table on the car. Did you draw anything else? What'd you draw? Did you draw that arrow the same size as the arrow that you drew on the weight that was hung? You should have. They represent a Newton's third law pair. The tension is the same everywhere in the string. Now, here's the thing. The tension isn't created just because of the mass that's hung. It's created because of both objects. Both objects contribute to the tension. You won't believe that the first time we deal with this, but you should believe it when you get the numbers back. So let's work this problem. In fact, you should work this problem. We've done this a couple times. But I'm going to add a little wrinkle here. It's not much, but if you want to be successful with these, you're going to have to find a way to be consistent with direction. As I said to you before, I would always make the direction of the acceleration positive. So I'm going to use the pulley as the place where I determine what I think is positive. I think it's going to accelerate in this direction around the pulley. Do you guys agree? I'm going to make that the positive direction, which means downwards the positive direction for the block, and to the right is the positive direction for the car. Be careful with these. This will change a little bit second semester. There are forces acting on the pulley, and we are ignoring them. That's because the pulley is massless and is not contributing any inertia to the problem. Alrighty. Is there any chance that the mass hung is going to accelerate different than the mass of the car? Can it accelerate faster than the car? Not without the string snapping or stretching. If the car moves 1 meter and the weight moves 1 meter, then they share the same motion variables. So A for the car will be the same as A for the mass hung. Now the rest of this should be easy, guys. I mean, you should be able to say, okay, MHG minus tension equals MHA. Right, that shouldn't be a stretch, is it? And although you can write out normal equals MCG, unless there's friction here, I don't know that we're going to use that for anything. On the other hand, tension equals MCA, that's probably going to be used for something. Now that's what Newton's laws do. That gets you to the end. Now you have to consider, well, what's the question? What are we being asked to do with this? Would it not be crazy to try and figure out the acceleration here? Seems pretty reasonable. You could do substitution. Do you want to do substitution, or you just want to add the two equations together? Okay. Add the two equations together, the tensions cancel out, and I'll get MHG equals MHA plus MCA. Now, I want to stop right here to remind you of something I said earlier today, that when you're doing problems like this, there should always be a point where you reach net force equals mass times acceleration. The external force here was the mass that was hung. All right. In a multi-body problem, you're trying to see how the motion of one object affects the motion of another. So is what I would refer to as a train question, in that you have maybe a group of objects that are connected by some kind of coupling mechanism. So I'll have a couple train cars here. All right, so let's say that there's something that couples the two cars together, and we're going to pull this way on the car on the left, and we're going to apply some force to pull the car. So this would be like the first car after the engine, and this would be the second car after the engine. Does that make sense? And the engine's doing all the pulling, and we're just leaving the engine out of the problem. Does that make sense? And we're applying a force, say FA. So there's a lot of potential questions here. But the first I want you to consider is there's a coupling mechanism that holds the two cars together. Now, I think this will be obvious, but let's start by giving us some naming. We'll name one M1 and M2. And I put them on wheels for a reason, to try and suggest that perhaps for the time being we'll ignore any friction. All righty, back to work here. And let that be a lesson to all of you people. No crinkles. I can't stand a crinkle noise. Just get it open already. So you guys should do the next part. You don't need my help for this. Draw a free body diagram. Remember, in your free body diagram rules, every object is treated as a single object upon which you deal with the free body diagram. So I think there's two objects here. All right, that's all the time I really want to offer for this, because it shouldn't take very long. Let's start with car number 2. How many arrows did you draw? So I'm thinking everybody should have a downward arrow, maybe M2G. That look good? Did you draw an upwards arrow?
Yeah.
Maybe N2, normal force on car 2. So if you drew those two, what else did you draw? All right, so you decide to add a force of tension this direction. All right. Yeah, I think that's about it too. Now, how many arrows did you draw on car number 1? 4, excellent. So maybe a M1G, maybe normal 1, And applied force. Now, when you drew the tension here, did you make every reasonable attempt to draw that tension in such a way that it was the same size as the tension on the other car? I think it's probably pretty clear that these two constitute a Newton's third law pair. We would refer to these two forces as internal forces in that they are internal to the system. When we deal with a system, there will be internal forces and external forces. If we want to know if a system accelerates, there has to be an external force to the system. You can have internal forces that cause internal changes, but if the system's going to accelerate, there has to be an external force to the system. I'm going to try and make this more clear in a minute, but when I look at this picture, it clearly seems like the tension force is internal. It pulls in one direction on one object and in the opposite direction on the other. All right, next question. If the couple doesn't separate or stretch, is it clear to you that the motion of one car is related to the motion of the other car? Now, this is an important question, and it's not one that you should take lightly, but if this car moves a meter to the left, how far will this car have to move? I'm bringing this up because we're trying to see if their motion is somehow locked together. This does not have to be the case. You can have a case where the motion of one is related to the motion of the other, but not the same. And it's easy. A couple of pulleys, we can make that happen. But I want to be clear, in this case, you should ask, is the motion of one object linked to the other? If so, are they the same? I believe they are the same. So I will say that both objects are going to have a shared acceleration in this direction. In fact, I will make this the positive direction. So from here on out, the problem still proceeds the same way. You have two different objects, so you're going to set up a couple of force equations. I don't think the y direction is particularly interesting if there's no friction, so we could probably ignore it here. So I think net force in the x direction here will be equal to m1a. Be careful. Notice you need to make sure you identify which mass it is that you're applying Newton's second law to. So I'm applying it to m1. And for m1, there are two forces that act on m1. I have made the common positive direction to the left. So when I look at the forces acting on M2, I'm just going to have tension acting to the left, and it'll be positive. And that's going to equal M2A. All right, as I tend to like to say, that's what Newton's laws can do for you. Now, I don't know what the question is. The question could be any number of things. It could be, what is the acceleration of the system? It could be, how much tension is there between the two cars? Any one of these are fair questions. Or maybe they say, the cars are going to accelerate, but the tension can't exceed this value. What's the fastest they can accelerate? There's a variety of questions. What you have here is a method for maybe solving one of them. For example, what if they did ask for the acceleration? Do you know how you could get an expression for the acceleration? I mean, I think you could just solve this for A, but that would have tension in it, and we don't know the tension. They did give us the applied force, so we could eliminate tension. Now, substitution would probably be the way you guys are used to doing it, but you know that there's other ways to do systems of equations, right? One of them is we can just add these two equations together. Have you guys done that before? Yes. Oh, good. So I don't have to explain it. So when I add them together, I get something that looks like this. You guys are the ones who said you've added equations together, so I don't have to explain it. I'm good with that. Let me do one more thing. Let's factor out the A. We would have to do that anyways to solve for acceleration, but I want to have our first kind of thought. Look, the applied force doesn't know if there's 2 train cars behind it or 100 train cars behind it. That force that's trying to cause the system to move doesn't really need to know what's going on there. In fact, it could just be one box of mass M1 plus M2. That's pretty clear because that's what I have here, isn't it? I have a single unbalanced force equal to the mass of the system times the acceleration. Newton's second law applies to systems just as much as it applies to individual objects. If you know what the system is doing, you could probably, I don't know, save yourself a couple of steps and treat the system holistically. Now, if there's friction involved and other things involved, you might not be able to do stuff like this, but I hope that you can see that there's clearly a pathway to get to the acceleration that might be faster than breaking it up into small pieces. On the other hand, if you want the tension, you're going to have the acceleration first anyways. There's no way to get to the tension otherwise. I do want to talk about the tension for a minute, but is there anybody who has a problem seeing how we'd get the acceleration just by dividing both sides by M1, M2? Then let's do that real quick. This would be the acceleration. But if I wanted the tension, now that I have the acceleration, do you realize substitution could allow me to do that? Or I could have eliminated acceleration and solve for the tension. Usually, solving for the acceleration will be easier than solving for the tension directly. So I'd encourage you to solve for the acceleration. It'll probably be the fastest way to solve your problem. I do want to, though, do some substitution, and I want to find the tension. I'm going to use this particular expression to find the tension because it's so easy. All I got to do is substitute. So I'll find the tension equals M2 over M1 plus M2 times FA. I just substituted in. Look at this closely. This is the percentage of the weight, or percentage of the mass. Do you see it? It's the mass of one object divided by the total mass. So this is the percentage of the system's mass that M2 takes up. I'm saying this to you because if you want the tension between the cars to be the least possible, would pulling them this way, where the heavier car is first, be the right way to go? I'm sorry, the lighter car is first. Do you notice that in this particular scenario, tension equaled M2 over M1 plus M2 times the applied force? If M2 is the bigger car, that makes this tension the bigger tension. If I want to lessen the tension on the coupling device, I probably want to pull the heavy car first and have the light car behind it. Do you see this decision-making process? That's kind of like the last step in the question, making you consider what would you have to do to reduce the tension. That also suggests that if you have a whole line of cars, the tension's going to get less down the line. Does that make sense? We've only done one set of cars here, but you can probably imagine if there's another car here, that this coupling has to pull the two cars behind it, while this coupling only has to pull the one car behind it. Does that make sense? All right. In this example, let's state that there's a coefficient of static friction between these two boxes. But let's just to make this easy, make the floor frictionless still. Now, I have an applied force. One question I could ask is, what's the biggest force I can use to push the top box without having the top box slip off from the bottom box? Or I could say, what if I want to push on the bottom box, what's the biggest force I can apply before the top box slides off the bottom box? Right, both cases present the same problem. Do you guys see the problem? Now, in fifth period, we did the problem where we pushed on the top box. Did it thoroughly. This is a challenging question. Let's do the problem where we push on the bottom box in this class. Now, there's no friction between the bottom box and the ground. However, there is friction between the two boxes. I think like anything else, we try and get an idea of what the system's going to do. I think it's not a huge stretch to suggest that there's going to be an acceleration of the system in this direction. Would you guys agree with that? Excellent. So we're going to accelerate this way. I'm going to make this the positive direction then. And then I would go ahead and ask you, the only way there's an acceleration in this direction is if the net force is greater than 0. I think we have a net force greater than 0. Let's go ahead and name this top box, so massive T, and this one bottom box. Now, a few of you in here probably can see through to the next part of the problem and probably in your head can figure out that that's probably going to be true. But I want you to do our process. I want you to draw a free body diagram for both boxes. I'm not saying don't use shortcuts. I'm saying I'm not going to let you use a shortcut this moment. Do the problem. Let's make this the top box and this the bottom box. Take a minute and draw a free body diagram for each box. That should be enough time, but let's start with the bottom box. I think the bottom box is probably easier. Let's get the low-hanging fruit out of the way and applied force that way. Did you have the weight downwards? That good? Did you have a normal force upwards? I'm making the normal force greater than the weight, and I'm doing so on purpose. Are you? This normal force supports both the bottom box and the top box. So I need to ensure that I am being mindful of that. But I also know that the net force in the y direction has to be 0. So there's got to be another force, and there should be a normal force downwards. This would be the normal force from the top box on the bottom box. Anything else? I think there is. I think there's friction between the two boxes. Remember, we're pushing the bottom box to the right. Inertia suggests the top box is going to want to slide this way off the top surface because it has inertia, suggesting it's going to cause a frictional force in this direction. At the same time, the only way the top box accelerates to the right is if there's a force on the top box to the right. What force is causing the top box to accelerate to the right? Friction. In this case, the static frictional force created by the top box and the fact that it's in contact with the bottom box is a Newton's third law force. It's an internal force to the system. Now, we still have other forces acting on the top box. There's also this force, the other Newton's third law force. It's in the system. The top box pushes on the bottom box, and the bottom box pushes upwards on the top box. than mtg. I think those are our free body diagrams. Maybe a little more complicated than what we've seen in the past. Now, I do think we're going to be interested in the forces in the y direction, at least on the top box, because that's creating the frictional force. In fact, I'm going to write that over here just to remind myself that I should probably be paying attention to this. But the top box is going to accelerate, isn't it? It's got an unbalanced force acting on it. I would expect that we would have something like this. The only force that can possibly cause it to accelerate to the right is the frictional force. Well, on the bottom box, now here's the question. Is this acceleration on the top box the same as the acceleration on the bottom box? Are they the same? Only if we want them to stay together. Do we want them to stay together? Yes. Yeah, that was the whole point of the problem. With how much force can I apply to the bottom box so the top box doesn't slide backwards? So I need it to accelerate the same rate as the bottom box. This is a tough set of things to think about. If the two accelerations aren't the same, then they're not moving at the same rate, then one's sliding past the other. So yes, I do want them to be the same. Now, there is this obvious thing that I hope is about to show up that you were expecting. If I add these together, we get the acceleration. This has to be the acceleration of the system. Right? You see what I'm saying? This has got to be how the system accelerates. This doesn't answer the question. This is the obvious. If I apply a force and both boxes do stick together, this is going to be the acceleration of the system. In fact, we know the acceleration of the system if they stick together. It's a big if. If they stick together is related on something else. Everybody see where I got this from? If not, talk now. Thank you. So what I did was I reminded myself that the frictional force on the top box is based on the normal force on the top box. In the y direction, the normal force on the top box minus mtg has to equal 0. So the normal force on the top box has to equal mtg. So I just did substitution. Does that make sense? So we now have our condition that has to be maintained. The static frictional force must be less than or equal to mu s times the normal force. So if I want to figure out the size of that frictional force, I'm going to have to find a way if I want to find out the size of the applied force that will be okay to push the box, I'm probably going to have to do some substitution to get there. I do recognize I could make that substitution. I think this is top-level thinking, folks. This is hard stuff. But I could make that substitution, couldn't I? Now this cancels out mt. And says that my acceleration has to be less than or equal to mu s times g. Well, I have this. Can't I substitute here as well? Now I've done it. I have put together a relationship that has my given information in it and tells me how big the applied force can be. It says that if I want to make sure the boxes do not slide with respect to each other, then I need to keep the applied force less than that. Not terrible? I don't know. I think this stuff is kind of tough. Got one more. You ready? Said 3. So, an Atwood machine is a pulley. And there's a number of ways I can draw the pulley. We're going to say that the pulley is connected by its center with a frictionless axle to the ceiling. And that we're going to hang a box on each side of the pulley. Like so. We'll say this is M1, M2. Now, for today, we're going to deal with only frictionless and massless pulleys. This means our pulley has no inertia. Now, the massless part, please put this in your notes. If a pulley is massless and frictionless, then the tension on the string used on the pulley is the same everywhere. If the pulley is frictionless and massless, then the tension is the same in the string everywhere. Now, let's assume that M2 does not equal M1. Will this system accelerate? All right. Now, you have to choose what direction you think the system is going to accelerate. And I've intentionally made M2 look bigger than M1. Don't assume that in a problem, of course. You know, listen to what the problem tells you. But let's go ahead and assume that we have to pick a direction for the acceleration. Now, I've said this the whole time, that if you think there's an acceleration, choose a common direction for positive and make the positive direction the direction of the acceleration. Would you agree that if this box accelerates down, this box has to accelerate up?
Yeah.
What I generally do for this is I draw the direction of the acceleration on the pulley to let me know that I'm applying this to the entire system. The system is going to accelerate the pulley and both boxes. But what I'm also saying by drawing that arrow is that I'm making upwards positive on the left side and downwards positive on the right side. Now, free body diagrams, be careful. I made a statement just a minute ago, and we have to conform to all of these. For example, tension upwards on the left side has to be equal to tension upwards on the right side, because this is a massless, frictionless pulley, so both tensions have to be the same. But it accelerates upwards on the left side, so that tension better be greater than the weight on the left side. And the weight better be greater than the tension on the right side. Your diagrams will be judged for this kind of consideration. Make sure that you do. Now, if there's only one string and boxes are connected together and the string doesn't stretch, can we agree that the acceleration of one box Has to be the same as the acceleration of the other box? Excellent. So T minus m1g equals m1a. Write that here. T minus m1g equals m1a. And on the other side, m2g minus tension equals m2a. Please notice I changed the direction for positive on the other side. Positive is downward, so the weight is positive and the tension is negative. We've exhausted Newton's laws. We've generated two relationships that could probably tell us what's happening in the system. If I wanted, say, the acceleration, do you see a pathway to get there? I could add these two things together, couldn't I? I'll have a positive tension and a negative tension. Won't those cancel out? So m2g minus m1g on the left side equals m1 plus m2 times a on the right side. Please look at what we have here. Net force equals mass of system times the acceleration. Do you see it? Gravity pulls down on both sides, but it's pulling in a positive side on one side and a negative side on the other. They're battling it out to see which one's bigger. Do you see it in there? But the acceleration of the system is still dependent on both masses moving. So if I want the acceleration, well, I'm just going to have to solve for it. I just divided by m1 plus m2. I reversed them a little bit to match up with the top. But you got a negative sign. That tells you a bunch. First, is there an acceleration when the two masses are equal? If the two masses are equal, I don't think so, right? The top's going to be 0. We kind of knew that. If you hang the same weight on both sides, would it accelerate? No. Only accelerates if they're different. If m2 was smaller than m1, then wouldn't this be negative? It'll go the other way. We're not surprised by that, are we? It tells us all the things that we would expect, but don't discount the fact that the entire inertia of the system requires knowledge of both masses. Of course, it seems to me like an important thing for you to do would be to come up with an expression for the tension and show that it's greater than m1g and less than m2g when m2 is greater than m1, which is what we assumed. Now that's going to be a little complicated. You're going to have to pick one of these to do so. It's not pretty, but I think you guys could do it. You're pretty sharp individuals.